Right. Another interesting fragmentation pattern, fragmentation that can occur with ketones is a rearrangement mechanism. And so this is exactly the same spectrum we saw before of the ketone 2-hexanone. And so what I want to do now is not explain the peak at 43, the base peak at 43, or the peak at 85 from alpha cleavage, but I want to explain what's happening, what's giving rise to the peak at 58. And the giving rise to this peak it's a result of a rearrangement mechanism. And the name of the rearrangement is a Mclaughter rearrangement. So this is how it works. If you have a ketone that has a gamma hydrogen available to it, then this Mclaughter rearrangement is possible. So what is a gamma hydrogen? Well, we need to be able to follow the chain at least to the gamma position, and there needs to be a hydrogen at that gamma position. So here's the alpha position, the beta position, the gamma, and yes, in 2-hexanone we do have a gamma hydrogen. We cannot work on the left-hand side for the Mclaughter rearrangement for 2-hexanone. We cannot do that because there's only an alpha hydrogen available. There are 3 alpha hydrogens available, no beta, no gamma hydrogens. Okay, so you need to be able to, in order to do the mechanism, need to be able to draw it so that a gamma hydrogen is in proximity of the oxygen. Of course, our high energy electron is going to knock off a lone pair, not pi electrons or sigma electrons, but lone pair electrons, because we've got lone pairs available. And so I'm choosing to knock off this electron over here and leave a positive charge here. Of course, this here is our molecular ion. So what happens in the Mclaughter rearrangement is we only use fishhook arrows, we only use single electron movements. What we can do is we can pair up this electron with one of these bonding electrons, so that will cleave that bond, break the bond. So if we can get one of the CH bonding electrons to pair with it, we can then form a bond between the oxygen and the hydrogen. And of course the remaining electron ends up on the closest carbon we have. And so you have movement of that gamma hydrogen onto the oxygen atom. Okay, of course the unpaired electron is here, and so how can we deal with it? And so to pair that up, we can cleave this bond here, which is beta to the carbonyl. We can cleave that bond and use one of those electrons to pair with that. And this is highly favored because if you pair those up, you get a stable alkene. And then of course the remaining electron is going to end up on the fragment which has a positive charge. This is driven by the formation of a very stable alkene. So this is propene over here. It has no charge, it's got no radical, but because it's got no charge, it will not appear in the mass spectrum, but it will contribute to what we see in the mass spectrum because of its stability. However, what we have is another fragment that has a positive charge, and we can calculate its mass as being 58. Its charge is 1, so 58 over 1 is m over z 58, and that really nicely explains the peak at 58 in the mass spectrum of 2-hexanone. So, in other ketones, there will be variations, so there will be different substitutions on the gamma carbon, but the mechanism will remain the same. So you can imagine with other ketones, if there's a gamma hydrogen present, that this hydrogen here and this methyl might change, but the core that's involved in the mechanism will remain the same. Of course, you might have different substitutions here, but in compounds that have the Mclaughter rearrangement available to them during fragmentation, this here is the mechanism that you will need to follow with slightly different substitutions all the way around.